inside out. Yeah. So quick overview of the talk structure. Git ultimately is a graph, and it's this graph that dictates Git's behavior. So if you understand this graph, then you understand Git. So we're going to run a bunch of commands on a Git repository, and then observe how those commands change the Git graph. So let's start by creating a project. So we make a directory called alpha to contain the project, and then cd into that directory. We're going to make a directory called data inside the alpha directory, and inside that create a file called letter.txt that contains the character A. So quick overview. I've got an alpha directory which contains our entire repo, and then inside that a data directory, then inside that a file called letter.txt that contains the character A. So let's initialize this as a Git repository. So we'll call git init, and here's what we had before. So here's alpha with the working copy. The working copy is the data directory and the letter.txt files. They're our files. And then there's the .git directory, which is not our stuff, that's Git stuff, and it contains everything that Git uses to do its job. So let's add that new file to Git. So we're going to add letter.txt with git add. And some stuff has changed. So what's going on here? Well, we've got the .git directory and the objects directory. That was all there before after we ran git init. But now we've got a new folder called 2e, and inside that we've got a file called 65. So what the hell is that? Well, a quick digression about git hashes, or hashes in general. So a hash is a way of taking a large piece of information and condensing it down to a unique identifier for that piece of information. So, for example, you can take the novel of Anna Karenina and hash it, and you get a 40-character string, maybe, that uniquely identifies Anna Karenina. So what it means is that, in theory, nothing else hashes to the same thing that Anna Karenina hashes to. And Git uses hashes extensively to identify pieces of information. So, for example, if we use Git to hash the contents of the letter.txt file, then we get the hash 2e65. Now, like I said, Git hashes are actually about 40 characters long, but I've just shortened them all to 4 characters just for clarity in the presentation. So this is making a little more sense now. So we've got the 2e folder, which is the first part of the hash, and the 65 file, which is the second part, inside the objects directory. So let's try and cat that file, the 65 file, and it's just not very helpful, unfortunately. It's compressed. But we can use this simple command called git cat file, which you just give it the hash of something in your objects directory, so for example 2e65, the hash that we put in originally, and it will give you back a human readable form of whatever you saved away. So there's A. So the second part to adding a file to the index, so remember this all started with git add. The second part, we've added a blob object which stores the contents of the letter.txt file. Now we make an entry in the index. So here's the index file, and unfortunately, again, when you cat it, you don't get anything super helpful. But you can use the ls-files command to give you a human-readable version of the index. And so you can see that our index has one entry, and the first part of the entry is the file path of the file that we added, and the second part is the hash of the content at the moment that we added it. So there's our old friend 2e65. Now let's re-add a file to a repository. So here's where we were, or where we've got to up to now. So this is a sort of notional representation of the Git graph. So on the left we've got the working copy, which has one thing in it, the letter.txt file, and that points at the content, A. So that grey square represents the content of the letter.txt file actually on disk, so our working copy file. And then on the right, then there's the representation of the index. And again, there's one entry, and it points at that A blob that is now in the objects directory. So that blue blob represents the blob that's inside the objects directory that we created. Now let's add a new file inside data also called number.txt and put 1, 2, 3, 4 in it. So we've updated the working copy now. We've got this new file with 1, 2, 3, 4 in it. Now let's git add number.txt, and now there's a new blob been created, 1, 2, 3, 4, and a new entry added to the index which points to that blob. Now let's change number to read 1. So it did read 1, 2, 3, 4. Now it reads 1. So in the bottom left of the working copy, then we've now updated that to 1. And of course we can re-add that to update the index entry. So the old existing 1, 2, 3, 4 blob, that carries on being the objects directory. It's very happy, nobody's punching it, it's okay with that. And now the index entry for number.txt has been repointed at the new 1 blob. Okay? Now let's make a commit. So I'm going to do a commit for the message of A1, and all the commit messages will look like this. So I have a character A, which represents the contents of the letter file, and a character 1, which represents the contents of the number file. Okay? So here's where we were before the commit. Here's our graph again, without the working copy or the index. So we've just got these 2 blobs, ultimately, the A blob and the 1 blob. And when we did that commit, a bunch of stuff happened. A bunch of new objects got created in the objects directory. So here's our first customer. This object was hash 0EED. It's got 2 entries. Number 1 is it says, hey, there's a blob. It's got this hash, and it was called this. So this, of course, represents the letter.txt file inside our working copy. So what we're trying to do here is we're trying to represent the contents of our working copy and its structure in the objects directory. So we've successfully saved the content of those 2 files in those 2 blobs, which is great. But there's no indication that those 2 files existed in files called, or those 2 pieces of content existed in files called letter.txt and number.txt. There's no indication that they were inside a data directory or anything like that. So the rest of these files, they all represent that. So we can see that this first file represents the contents of the data directory. Okay, so it's got 2 entries, 1 for letter and 1 for number. And that's now in the object directory. Now there's another new file that has 1 entry in it, which is a tree, which is called data. So this, of course, represents the contents of the alpha directory, the top level of the root code. So let's add that to our graph. So what we're doing here again, like I say, is representing the structure as objects. Now there's another new file as part of doing this commit, the commit object. So we can just cat that, it's just inside the objects directory, just like everything else. And it's got a few interesting things. Number 1, it's got a pointer to the top of that tree graph that we created. It's got the author, it's got a timestamp, and it's got the commit message. Okay? So let's add that to our Git graph. So now we're kind of seeing the shape of where things are. We've got the pink commit object, A1, which points at its content. Next, step 3 of committing, we point head at the new commit. So let's try and cat head, and that's totally a file on disk. It's inside the .git directory. It's called head. We can see that it contains ref/head/master, which looks like a file path, and it actually is. So let's try and cat that file. So we cat .git/ref/head/master, and we get the hash of that A1 commit. Okay, so this is just a file on disk. It represents the master branch, and so now we can add a pointer to the master branch to the graph. Okay. So we've got master, which points at the A1 commit, which is to say master's on the A1 commit, and then the A1 commit points at its content. Okay? Let's pop back to head for a second, and now head is making a little more sense. Head just tells us what branch is checked out. So it just contains a reference to the master branch, and therefore head points at master points at the commit, and so on. Okay? Now let's make a commit that is not so so here's where we were, just a quick summary. I've added back in the working copy and the index. So the working copy, 2 separate files there. Notice how the index ultimately points at the 2 blobs that we've got. Okay? Now let's change number to be 2. And let's do git add. So I'm sorry. So when we change number to be 2, then the entry in the working copy in the bottom left there, that grey box, changed from 1 to 2. Okay? And now when we add that file to Git, then of course we're going to update the index again. So now the index points at that new 2 blob that got created as part of the add step. Okay? So here's where we are. Now let's do another commit. Let's make the A2 commit. So again, let's follow through those commit steps. Number 1, make the tree graph of the contents of the index. So take the index and turn it into objects. Okay? So here, looks pretty similar. It totally is pretty similar, except this time the data tree object points at A, but the original A blob, and this new 2 blob. Then step 2, create the commit object. The main interesting thing here is that it's got a parent. So the A2 commit on the bottom right there points at its parent, the A1 commit. We'll see that that's handy in a second. Next step, point head at the new commit. Now, we're not actually repointing head. Head just stays pointing at master because we stay on the master branch. Remember, master is just a file on disk that contains a hash. That hash used to be the A1 hash, now it's the A2 hash. So what have we learned from this? Well, number one, content is stored as trees. And this means that the objects database stores diff. So we were able to reuse that A blob from the A1 commit in the content of the A2 commit. And you can imagine that reuse will be much more pervasive for larger repos. Next, each commit has a parent, which means that a repository can store the history of a project. Next, refs are entry points for the commit history. And this means that commits can be given meaningful names. So the A1 message or the A2 message, let's say, that's a fine message. It's helpful it tells us what that commit does. It doesn't really tell us what that commit's place is in the whole repo. Whereas master is great. It tells us, hey, this is the state of the art of this repo right now. Next, objects are immutable, which means that content is edited and not deleted. So it's pretty hard to lose content with Git because those objects mostly just stay inside the objects directory very happily and safely. So you can always find them eventually. Next, though, refs, unlike objects, are mutable. So what this means is that meaning of a ref can change. So master may point to A2 right now, but in the future it will point to A5 maybe, and that will be the new state of the art of our repo. Now let's check out a commit. So normally when one checks out branches, we're going to check out a commit. So the way we do that is just give it the hash of the commit we want to check out. There it is. So this is the hash of the A2 commit. Now this is a bit weird because we've already got the A2 commit checked out, right? So what's the point of this? Well, let's see. So we're on A2 via the master branch. Now we're going to be on A2 directly. And that has some funny ramifications. So head is the tag. Let's look at what happens. Check out step one. We write the commit tree to the working copy. So we just take whatever the content of the commit we're trying to check out is, and we just write it to the working copy. Now there's no change here because we're just staying on the A2 commit. So the working copy carries on being A and 2. Next, write the commit tree to the index. Again, no change here because the index, we're still on the A2 commit, so it's still just A and 2. Next, we point head at the thing that was checked out. Now there is a change here, which is cool. You can see that when I cat head, it's got a hash in it. It doesn't have ref/head/master in it anymore. And this is what it means to have an attached head. So it just means that your head doesn't point at a branch. It points directly at the commit. And so we can see that in our Git graph. We can see that though master still happily points at A2, then head points directly at A2 rather than at A2 via master. Okay? So that's cool. Let's change number to be 3 and commit that. We're still in the attached head state, which makes sense when you think about it. So look at how now head points directly at A3 rather than A2. Now let's create a branch because that A3 commit, that's fine work. It's not on a branch, which means it's easy to lose track of it. Okay, so we don't want to do that. So we can create a branch to solve this problem. So we create a branch called deputy, and deputy is just another file on disk, just like master. So it just contains a commit hash. It's super easy. So that is the hash of the A3 commit. So now we've got in our Git graph, we've got deputy pointing at A3 as well as head, which means that the A3 commit is now safely on a branch. We're still in attached head state though. So what have we learned from this? Well, branches are just refs, and refs are just files. And this is why people say that Git branches are lightweight, because if you ever want to branch, then essentially what happens is a new file is created, and the hash that head is pointing at is put inside that file, and that's it. So that's insanely fast. Now let's check out a branch. So let's check out master. So before we checked out a commit, now we're checking out a branch. And let's follow through those checkout steps again. So here there is a change to the working copy. It did read A and 3, now it reads A and 2 because we're moving to the A2 commit, which is what master is on. Then we write the commit tree to the index. Again, we've got a change here from A and 3 to A and 2. Next, point head at the thing that was checked out. We just point head at master, which means we're back on a branch, and so our head is no longer detached. Now let's do some merging. Let's merge an add system. So I'm going to check out deputy just as prep for this. So the important point here is we're on the A3 commit, and we're going to try and merge the A2 commit. So we're on A3, we're going to merge A2. And when we merge master to do that, then it says already up to date, which means nothing happened. So there's been no change at all to the Git repo. And the reason for this is because a commit is a set of changes. So if you cast your mind back to when we were on the A1 commit, then we made some nice changes to the working copy, and then we committed them produce the A2 commit. So we use a set of changes to produce a new commit. Now, given that we're now on A3 and we're trying to bring in A2, then what does that really mean? It means we're trying to bring in some sets of changes, the A1 and A2 changes, but they're already in our history. So that doesn't make sense to make any changes. We've already got those changes incorporated into our graph, so why bother? And that's why Git, if an ancestor is merged into a descendant, then Git does nothing. Now let's merge a descendant. So let's check our master just as prep. So now we're on the A2 commit. That's the important one here. We're on A2, and we're going to merge in A3. And there was a change there, okay? So do you see that? There, okay? So what's happened is a fast forward. And ultimately a fast forward means there's already a commit that has the changes I want. Therefore I can just fast forward my ref to that new place. So the master used to point to A2, now it points to A3. And let's just think through why that is again. So a commit is a set of changes. So this is back before the merge again. So we're still on A2, we're on master. And we're about to merge in A3. Okay, so a commit is a set of changes. So there were some changes that, we were on A2, and then we made some changes back in the day, and then committed and produced the A3 commit, right? That's what all happened before. And now we're trying to merge the A3 commit. So the thing is that there's already a commit that embodies the changes we want to bring in. It's just the A3 commit. So we can just repoint our master at that commit and say, this is where master is now. There's no need to meddle around with the commit history or create any new commits or anything like that. So that's why this is a fast forward commit. Which is to say, if a descendant is merged into an ancestor, history is not changed, no new commits, but head is changed. Okay, so head got repointed to this new commit, to the existing commit. I'm sorry. Now let's just change number to be 4 and commit that, and then check out deputy and change letter to be B and commit that. So I know it was through fast, but it's okay. We'll step it through. So we were on A3 before. Now we've got 2 new commits. There's B3, where letter is B and number is 3. And then there's A4, where letter is A and number is 4. So the important point here is that in one new commit, letter was changed, and in the other new commit, number was changed. Okay. And we're on deputy, so that's it, on the B3 commit. Now, what allows this? Well, commits can share parents, which means that new lineages can be created. So this is how this is allowed. So B3 and A4, they both have the same parent, which is just A3. Now let's merge 2 commits from different lineages. Okay? So commits can have multiple parents, which is what allows this. So this is where we're going. We haven't got here yet, but we're going here. So we've got the B4 commit, which we're going to create as a result of the merge. And the reason this is allowed is because lineages can be joined with a merge commit. So B4 is going to have 2 parents, B3 and A4. Okay, that's what joins these 2 lineages together. Now let's do the merge, and it just says merge, so that seems to go okay. What are the steps? So this is where we're going. Let's walk it through. Now, commits have parents, which means that it's possible to find out the point at which 2 lineages diverge. So the B3 commit and the A4 commit, they're both the start of 2 new lineages, 2 separate new lineages. But they did come from the same place. They came from the A3 commit. And it's possible to find that, if you like, most recent common ancestor, it's sometimes called, or base commit. So now let's bring the 3 actors on stage. So we've got the base commit, the A3 commit, where both of our commits we're merging came from. We've got the receiver commit, B3, which is the one we're on, and the giver commit, A4, which is what we're bringing in. So let's step it through. So first we want to generate the diff that combines the changes made by the receiver and giver. Okay? So what this means is, we want to take the changes that the receiver made, take the changes that the giver made, and bring those together. So if we just recap, the receiver changed letter from A to B, and the giver changed number from 3 to 4. We just want to merge those 2 sets of changes together. And so if we consider the changes made to letter, then letter was A in the base, B in the receiver, and A in the giver. Now, a merge has a base commit, as we've already discovered, which means Git can automatically resolve the merge of a file that has changed from the base in only the receiver or the giver. So this is exactly the case that we're facing here. So letter was changed from A to B in the receiver, but it stayed the same in the giver, which means that the new diff is just change letter to B. Super easy. Same story for number. This time it was the giver that made the change, but that doesn't matter. The diff is just, hey, let's change from 3 to 4 in number. Now step 2 of a merge, apply the diff to the working copy. Super easy, we just follow the instructions in the diff, which is to say change letter to B and number to 4. And then step 3 of a merge, apply the diff to the index. Super easy, just change the entry to B and 4. Now the updated index is committed. The main thing to note here, 2 parents. So the B4 commit has B3 and A4. And then next, finally, just point ahead at the new commit. So now deputy is on the B4 commit. Okay, so that was merging 2 ancestors from 2 different lineages. Now let's merge commits from different lineages, so the same as what we just did before, but where the commits both modify the same file. So something terrible coming. So we're just going to check out master and then merge and deputy just to bring ourselves up to date. So the point is both deputy and master are now on the B4. That's all we care about. So let's check out deputy, change number to 5, commit that. Check out master, change number to 6, and commit that. So here's our 2 new friends. We've got B6 where number is 6, and then we've got B5 where number is 5. Okay, so the point here is number was changed in both of them, which is fine. Now let's merge deputy, and we got a conflict. So it says, hey, there's a conflict in number.txt. So let's just follow through the steps again, nice and easy. So we generate the diff that combines the changes made by the receiver and the giver. So the letter file, easy peasy. No diff at all. Everyone says B. We're locked down. So there's no diff. Number.txt, unfortunately, the story is different. So in the base it's 4, in the receiver it's 6, and in the giver it's 5. Okay? So let's think about what Git wants to do at this point. It just says like, oh hey, so I'm going to write a diff where number is changed from 4 to 6. That seems pretty okay. And oh hey, I'm going to write a diff where number is changed from 4 to 5. That seems pretty okay too, but unfortunately those 2 changes aren't compatible. So that's what produces a conflict. So the diff is, let's change number to 6 and let's change number to 5, which obviously doesn't work. So this Git just kind of merrily marches on, just trying to get through the whole process. So it applies the diff to the working copy, and that sets number.txt to look like this, which I expect you've seen before. So Git just says, hey, I'm just going to give you both versions and just let you sort that stuff out, yeah? And then Git applies the diff to the index as well. So here's what the index looked like before the merge. And I kind of lied to you a little bit when I said that an index entry is just a file path and a hash. That was true, but it's also a number. And that number is called the stage. And every time up to now, all of our index entries have had a stage of 0, so everything's been absolutely fine. Stage of 0 means unconflicted. Unfortunately now this is what the index looks like. So letter still fine, no conflicts there, it's still a stage of 0. But number is now entered in 3 times. So it's got a stage of 1, where the hash is the content in the base. Then it's got a stage of 2, where the hash is the content in the receiver. And then it's got a stage of 3, where the hash is the content in the giver. It's the presence of these 3 entries that tells Git that it's in conflict. So let's just carry on. The user resolves the conflict in the working copy. And their solution is just to say, well, 6 plus 5 is 11. So I'm going to set number to be 11. And then the user resolves the conflict in the index. And the way they do that is just git add. So in this context, git add means, hey, I want to resolve these conflicts. Everything's fine now. So here's the index after we resolve the conflict. So now the letter entry is the same, but the number entry, stage of 0, which means unconflicted, which is great. And that hash is the hash of the 11 content. So now the user commits the merge as B11 and everything's okay. So there's the B11 commit, bringing those lineages together. Now let's remove a file. So here we were after the B11 commit. The working copy had B and 11 in it, and the index had B and 11 in it. The user runs git rn /.txt. And this removes the file from the working copy. So it just deletes the file as this. So letter.txt is now gone. Okay? And it also removes an entry for that file from the index, or the entry from that index. So now the index just points at the content of number. Which means that, excuse me, when the user commits, then remember how a commit works. It just walks the index and produces a tree graph of its content. So that index no longer has an entry for letter.txt. .txt in it, which means that the entry is going to be completely missing. So now the new tree graph just points at 11, it doesn't point at .txt. Okay? Let's copy a repository. So we're going to use CP to do this first of all, not Git. So we're going to cd into the directory above, and then cp alpha to a new repo called Bravo. So here's what's happened. Alpha had a nice working copy in a .git directory. Now Bravo has exactly the same thing. This is a complete facsimile. Okay. So here's the two Alpha and Bravo repos. They're both on the 11 commit. Let's connect a repository to another repository. So cd back into Alpha, and we're going to do git remote add. And git remote add says, hey, git Alpha. It turns out that there's a repo that's an awful lot like you. It's called Bravo, and it lives here. So it's just a relative file path. So what's the change? Well, now git config has been changed. So there's just a couple of new lines that say, hey, remote, it's called Bravo, it's at this URL. Let's fetch a branch from a remote repository. Fetching is all about saying, what's going on in this other repository? Let me get that stuff, bring it over here, but not integrate it into my stuff yet. So let me just put it in this kind of separate location and just keep it separate for now. Okay, so let's cd into Bravo, and let's change number to 12 and commit that. So here's where we are. Bravo is on the 12 commit, Alpha's still back in the Stone Age on the 11 commit. Let's cd back to Alpha, and we're going to do git fetch Bravo master. So let's walk through those steps. Step 1. Find the head commit on the repository being fetched, which is of course the 12 commit on Bravo that we're bringing in. Step 2, copy that commit and all its dependent objects over to Alpha. Okay, so now Alpha has the 12 commit and its tree graph and all that good stuff. But notice how Alpha's master is still pointing at 11, right? So though it's got the new object, it hasn't updated itself to point at the new commit. Okay. So for all intents and purposes, if you looked at Alpha, then it would look the same. It's just got these new objects. Step 3, point the ref for the remote branch at the fetch commit. Now what the fuck does that mean? Well, basically there's this new folder called remote inside .git/refs. And inside that there's a new folder called Bravo. Inside that there's a new file called master, which contains the hash of the 12 commit. Okay? So we've managed to super secretly save the contents of a branch on a remote repository in our local repository, which is what fetching is all about. So let's add that grep to our graph. So notice how Alpha's master is still on 11, but we've got this record of Bravo master pointing at 12. Okay? Next, we point something called the fetch head at the fetch commit. So let's just add that to the graph, also pointing at 12. And the fetch head is ultimately just a record of what happened the last time you fetched. So it just said, hey, I got master from Bravo and it had this hash. That's lovely. So again, there's the hash of the 12 commit. So what do we learn from this? Well, objects can be copied, which means history can be shared between repositories. And we've learned that repositories can store remote refs, which means a repository can record locally the state of a branch on a remote. Now let's merge fetch head. So we do git merge fetch head, and it's a fast forward. So fetch head ultimately resolves to please change your blah to this commit. So in our case, it's please change your master to this commit hash that I've got here. So that's the 12 commit hash. So the result is before merging fetch head, master was pointing at 11, and now it gets fast forwarded to 12. Okay. So now let's pull a branch from a remote. And we do get pull Bravo master, and it says already up to date. Again, no change at all. The reason for this is because pull is just shorthand for fetch and then merge fetch head. Okay. Let's clone a repository. So we're going to clone cd into the directory above, and then clone alpha to Charlie. So new repo called Charlie. Let's walk through the steps. Number 1, create a directory for the new repository. Create the Charlie directory. Number 2, cd into it. Number 3, call git init to create an init, .git directory for Charlie. Number 4, then check out whatever branch is checked out in alpha. So master was checked out on alpha, that's the thing we're cloning, so we just check out master on Charlie. And then 5, do a pull so that Charlie's master is in the same state as alpha's master. So there again is our old friend, the 12 commit. And so we can see that, master is now pointed at the 12 commit on Charlie. So this is pretty similar to that CPU we did. It's a little more efficient, but ultimately the same result. Now let's cd back to alpha. Let's create a new commit, 13, and let's add Charlie as a remote on alpha. And let's do push. So let's do git push Charlie master. So what that says is, let's push the state of alpha over to Charlie. Now, something good happens, writing objects happen. So we've kind of seen this pattern before. Here's before the push, alpha's on 13, Charlie's on 12. And after the push, then Charlie's got the new 13 commit. But again, master's still pointing at 12, so something didn't happen. And what happened was that Git said, hey, I'm refusing to update the checked out class because it will make the working copy inconsistent. Now, what's going on here? Well, just imagine that I'm making some changes to Charlie, and I'm typing some lovely changes into my working copy on Charlie. And then suddenly someone pushes alpha over to me. Now, a push is effectively a checkout. So what's going to happen is, it's going to send some new objects, which is great, but it's also going to say like, hey, your working copy, it now needs to reflect whatever commit was just pushed, right? So my working copy change is blown away, gone. That's terrible. And then, in a similar fashion, the same thing happens, but if I was making some changes to the index, if I was staging some stuff, then again, my index is going to be blown away with the contents of the hash that was of the commit that was just pushed. So that's no good. So Git won't push to things that are to branches that are checked out currently on the remote repo. But that doesn't make any sense because we push all the time, right? We push to GitHub. How does that happen? Well, it happens with bare repositories. Okay, so let's clone a bare repository, see how that works. So we're going to git clone a new repository called Delta. Now with the dash bare flag. So we're going to create a new repository called Delta. There's a complete clone of alpha, except it's bare. Now notice that when I look inside the Delta directory of our new repo, then there's no .git directory. Okay, so in fact the contents of the .git directory have just been puked in the top levels. Okay, so what does this mean? Well, it means that there's no working copy. So there's nothing for poor old Charlie or Delta to have messed up for them. Okay, so this bare repo has no working copy, which means that so they're both on 13, alpha and delta are both on the 13 commit. So let's cd back to alpha, let's add delta as a remote, this is all recap. Let's make a new commit called 14 and commit that. And so here we are, alpha is on the 14 commit and delta's still on the 13 commit. Then we do git push delta master, and this totally works. Everything is fine. So the objects get pushed over, so now the delta repository has the 14 commit, and then master gets updated to point at 14, so it's got the new stuff. Git is a graph. This graph dictates Git's behavior, which means if you understand this graph, then you understand Git.